Let us tackle this this Maclaurin Series 1. Before I forget to mention this, on this general term for the first derivative, I don't really need that summation notation there. As long as we have this right here, that's good for the general term there, and I'll explain how I got that. So yeah, this problem, these always look intense, but we got to battle through that there. We know how to do this. Let's just take it step by step here. So they give us a Maclaurin series, and then letter A says determine whether that series converges or diverges at x equals 6. So I simply took the x equals 6, plug that in for that x right there to get that. So then the 6 to the n's canceled out, and then I had this series. So this is like our normal, does it converge or diverge stuff there. So if I see some polynomials on that guy, I'm just going to do like my limit comparison test. Okay, so I'm going to subtract the highest exponents. I'm going to go n over n squared. I'm going to use 1 over n as my comparison series. I know when the p is 1, that's the divergent harmonic series. So that's a divergent p series. And then remember what our limit comparison test says. We're going to do a limit as n approaches infinity of the original series divided by the comparison one. Simplify that a little bit. We got 1 for that, n squared over n squared. These leading coefficients, because the degrees are the same, we got 1 for that, which is a finite positive number, which means both series do the same thing. So since that comparison series diverge, that means our original series will also diverge by that limit comparison test. So that is kind of normal, kind of what we're used to doing. Um, I did kind of mention this wasn't on the rubric at all. Like I would not do this, but if you're doing like a multiple choice or something, one approach is I did like a that over that over that, and that became 1 over n plus 1 over n squared. Now, 1 over n squared was a convergent p series. So like if you add them up, you're going to get a number for that. It converges. And then that was a divergent p series. So if you have like a diverge plus a number, that means you have like infinity plus a number. Like that's still going to be infinity, which is going to be diverged there. This method was nowhere near on the rubric. Like they're gonna want us to use like that limit comparison test. So this is like a real good way to handle that guy there. But just do that other way out there in case you're doing some multiple choice and you have to think on the fly and just doing the best that you can there. But this is the best way that we could do that problem. All right, now letter B. Wow, they just made this look so much more complicated than it has to be. All right. So, I mean, I see this, I see this, and then I see first three terms, and then I see, and I don't think I ended up using this guy at all, which is weird. But then this guy right here, when I saw they're subtracting the difference between like a partial sum. So I guess right there, they're saying the partial sum, but they're just saying this is the difference between like the actual value on the function and the partial sum using this Maclaurin series right here. So when you see that, that's the difference between an actual value and the Maclaurin series value, they're meaning for us to do an error problem. And then they also gave us a hint that they said to use the first three terms. So a lot of times on the error problems, we look at that next term. And so I see first three terms and I see this notation, the absolute value of subtract and stuff there. That's what told me that I was doing the error. Um, And so here's my work for letter B down here. So if I look at this thing here, so that's the thing that we're working with right there. Okay, so that's the guy. So I started with that. And then since I had like that, it's kind of like I could pull a 1/2 out that you really do have that -1 to the n or -1 to the n plus one notation. Like that's going to make it alternate. Even if it's like, even if you have just a geometric sequence and the r is a negative, that's going to alternate signs right there. But that negative to the n, that's going to be an alternating series. And then the terms themselves keep getting smaller and smaller right there. So this is the stipulation that allows us to just use the alternating series error bound and just look at the next term in the pattern, which we've done on some other tests as well. So we just want to kind of mention a lot of times it gives us this. It'll tell us a series is an alternating series whose terms decrease in absolute value to 0. But this time we just had to actually state it ourselves. So it's good that we're seeing something there because this part B, man, the first time I worked this through, I was like, that's looking pretty intense. So I thought on it for a second, and then what I did, I kind of skipped over and did letter C and D first, and then I kind of came back to that there. So we can use the alternating series error bound. You need to kind of mention this. That's the stipulations for that. And then we're just going to say, okay, the error is less than the absolute value of that next term. So since they used the first three terms, I knew the next term was n equals 4. So all I did was go to this guy and I just plugged in 4 for all of the n's. And so that's where I'm getting this work right here. This is typically always a no calculator issue there, but that's just 16 and then another 16. I knew that was 256. And it was a little bit weird because we're supposed to show that this error, this number here, this 5 over 256 is smaller than the 1 over 50. And a lot of times they'll make those really close to tell. But then I had to kind of recognize that 1 over 50 was the same thing as 5 over 250. And then I can easily make, since those numerators are the same, that 5 over 256 is smaller than that 5 over 250. So that thing is less than that 1/5 right there. So yeah, I thought that was a crazier part B, and they made that look so much worse than it actually did. But part C and part D, I felt was a strength of ours. Part A, C, and D, I felt are definitely strengths of ours that we could handle doing as long as we're working hard with these things. So I like letter C. It says find the general term for the Maclaurin series for F prime. So this is the general term for F. And so I wrote that down right there. And if I want to do the general term for F prime, we just need to take the derivative of this thing. So this is like a number. This whole thing is a number times x to the n. And so this is just you're doing the derivative of that. It's a number times x to a power. Just like if it's like 5x to the fourth, you're going to multiply by the power, decrease the power by 1. So all I'm doing here, this is the number. I'm going to multiply by that power so that I'm multiplying by that n and all that stuff is still there. And I'm decreasing that power by 1. So I'm just using my power rule for my derivative. And then the n over n squared would have canceled. So that's just that 1 over n. All the other stuff carries down. And so this is what you need for that general term right there. I don't need to have that summation notation. This is the general term for that first derivative. So that's the first thing that they want us to ask for. So I definitely like letter C a lot better. But then it also said find the radius of convergence for the F prime. Now, notice the original function. They told us the radius of convergence was 6. And so I just mentioned the radius convergence is the same as the original. You could just jump straight to the radius is equal to 6. So since the original one had a radius convergence of 6, that means the derivative one will also have a radius of convergence of 6. If you don't believe me, what I had to come do to come convince myself, and it does have that in the rubric, it's the same as the original, and you're allowed to go straight to it. I actually worked out. I actually took this guy right here and I did my ratio test with it just for fun. You don't have to do this, but see, I did my ratio test and then I did get that radius of convergence was equal to 6 right there. So it does work there. Like you are allowed to still do that, but you don't have to. So we're just kind of learning a little bit of a shortcut right there. All right, so then letter D. The last part, again, these look worse than they actually are there. You got to convince yourself that A, C, and D are some strength of ours there, okay? And then just deal the best you can with letter B. So G is equal to this. It tells us to use the ratio test. And we know the ratio test. We're good at the ratio test. And so I'm going to start with that. And I did the limits and approaches infinity. I'm going to first replace all of my n's with an n plus 1. So that's what I did there. Replace all of them with an n plus 1. And I'm dividing it by the original. So I'm going to multiply by the reciprocal of that. And remember, if we're going to find the radius of convergence, the ratio test converges when the limit is n approach infinity of the absolute value of all that stuff is less than 1. So then I just kind of simplified it the way we typically do on a ratio test. Rewrote that, cancel some things out, and simplified it there. So make sure you're practicing that. Make sure that works in your brain. And then what we do is we pull out all of the x's, all right, numbers and n's. You can kind of leave those in there. You can even pull out numbers and stuff there, but all the n stuff, because as that limits and approach infinity's got to stay in there. So I just pulled out the x's. I could have also pulled out like the 3 if I wanted to, but all that stuff is in there right there. So this is n cubed over n cubed. So those degrees are the same. So that limit answer is just going to be 1/3. And so you can move that 3 over. Even if that 3 was on the inside, you can still move that 3 over. And then I know it's like a nonlinear inequality right there, but you're just meant to figure out like that's got to be an x, and then that's got to be like that's like the standard thing. Get that x by itself in there when you want that radius of convergence. And if it says integral convergence, That's when you gotta make like the lesson sandwich and check the endpoints and stuff like that. But once you get down to that point, it's just like, hey, the absolute value of X is less than R. That's gonna be your radius of convergence. So that was nice. I was just meant to get to that point right there, and that's what our radius of convergence is. So just do the best you can with that, and we got to group together a few of those together and kind of study all those together. That'll be really helpful for us. Chateau.